Hello, welcome. We're going to do lab number 6, investigation number 1 today, where we'll investigate the effects of freely falling bodies. Now, to go over here, in your study of dynamics, starting in lab number 3, we saw that you had to apply a force to an object in order to get it to accelerate. And the forces that we applied in lab number 3 was a string being pulled by a falling weight. But the string was pulling the cart, so that's a contact force there. In lab number 4, we had the carts move because of a fan blowing. So the fan blowing against the air, pushed the cart along. So again, that was another contact force. But what we're going to look at now is objects that are in free fall. In our own experience, of course, we've seen that if we throw a ball up into the air, it will fall and land. But the question is, what's causing the fall? We see it accelerating. Where's the force? So that's where Isaac Newton comes up with his ideas of quantifying the law of gravity. People have known about gravity ever since there have been people around. Anytime the first person fell down, we've discovered gravity. But let's go ahead and do a quantitative analysis. Okay? Let's start off with activity 1-1, pardon the squeak, which starting on page 129, prediction 1-1, toss a ball straight up a couple of times and observe the motion as it falls downward. Describe in words how you think it might be moving. Some possibilities include falling at a constant velocity, falling with an increasing acceleration, falling with a decreasing acceleration, or falling with a constant acceleration. So I have here a softball, and I'm just going to toss the ball up into the air and catch it, toss it up and catch it. Okay? Now the question becomes, what happened to the ball as it comes back down? Is it coming back down at a constant velocity? Is the velocity changing? Is it speeding up? If it is speeding up, is it speeding up at a constant rate? Or is it speeding up at a changing rate? That's kind of tough to tell when an object is falling like so. Very tough to tell. Now we could do video analysis. That's one way of doing it. Another way of doing it is we can use our motion sensor here to actually track the position of the ball, calculate the falling velocity, and calculate the falling accelerations. See if that changes. So that's going to lead us to page 130. Start out on page 129. Prediction 1-2. Suppose you drop the ball from a height, releasing it from rest. On the axes below, sketch your predictions of the velocity time and acceleration time graphs of the ball's motion. So again, I take the ball here and I drop it. What happened to the motion? What happened to the velocity of the ball? What happened to the acceleration of the ball? Let us go ahead and define up be positive. So at the very least, as the ball is going downward, it has a negative acceleration. It has a negative velocity. Moving in this direction is a negative velocity. So now let's go ahead and quantify it. Let's actually do the experiments. So we have it all set up. All I'm going to do is I'm going to start with the ball here, and I'm going to let it fall. I've got 2 triggers set in. The first trigger is when the ball passes a certain distance away from the motion sensor. The second trigger is just before the ball hits the ground. So we should see, for the most part, only the motion of the ball as it falls. So let me move that there. And when I hear the clicking, I'll let it go. Okay, now let me go ahead and change the scale of the graph. And we can see something kind of interesting here. I'm going to go ahead and repeat the experiment because we had this weird thing occur down in this area over here, which is affecting the rest of it. So I'm going to go ahead and repeat the experiment and see if that comes back up again. That looks much better. So we'll go ahead and use that data. Now, a couple of things to take into account. Let me go ahead and move the camera so that it's over facing toward me while I'm doing the work. There we go. Okay, a couple of things to take into account. First off, if you look here, we see the acceleration drops down, the acceleration comes up. That acceleration is, let me disconnect this. We'll go ahead and disconnect that for a moment. That acceleration is calculated from data before and after. So we want to get rid of these two pieces of acceleration. We want to get rid of these two pieces of acceleration. So I'm going to go ahead and do that. And I have a function that allows me to delete data that isn't of any consequence, so to speak. Just that last one right there is really the one we need. Okay. So we'll go ahead and delete the highlighted data and get rid of the highlighter there. And let's go ahead. So there's the graphs that you have to sketch. All right. On the bottom of page 130, there's the two graphs. As we can see, it looks like the velocity is at a constant slope. Let's apply a little bit of smoothing to that to see if we can hold on to a constant slope there. Nope, we're going to go ahead and just leave it as it is. Let's take a look at the acceleration. Let's apply some smoothing to that. That's about the best we're going to get there as well. Okay, so we have our acceleration graph, we have our velocity graph. Now I have a couple of questions to ask. Question 1-1, what does the nature of the motion look like? Is it a constant velocity, constant acceleration, increasing acceleration, decreasing acceleration, or is it something else? And how do your observations compare with the predictions you made? Well, if we take a look, we see that it's not constant velocity because the velocity is changing, but it is constant acceleration because the acceleration is nice and flat. The next question is, what motion of a different object observed in a previous lab resulted in similar graphs to the ones of the falling ball? Describe what was moving and precisely how it was moving. If you look at lab number 2, I believe it was investigation 3, where we had a fan cart placed where we had the motion sensor located here, the fan cart was located here, but it was blowing in this direction. So it was moving towards the motion detector, which means it had a negative velocity, but it was speeding up as it was moving towards the motion detector, and it had a constant negative velocity. Okay, question number 1-3. Is the acceleration of the ball positive or negative as it falls down? Take a look at the slope of the velocity. We see a negative velocity slope here. So therefore, we have a negative acceleration. So that does make sense there. Let's do some quantifying then. Let's take a look at activity 1-3. For method number 1, we're going to use the analysis features to determine the average acceleration from the average of the accelerations. So I'll just click on the acceleration graph, click on the statistics, and we see that the average acceleration was minus 9.6 meters per second squared. Okay, that's fairly reasonable, and in fact, if I got rid of that last data point, it would probably be somewhat less, but fairly reasonable there. Now, let's take a look at method number 2. Using the fit routine, find the mathematical relationship between velocity and time during the same time interval. So we will highlight the data covering that same time interval out to about just under 0.3 of a second. And what we will do is we will do a best fit line using the fit function. Turn that on, select linear, and we see the graph is minus 9.67, you'll pardon me while I squint, minus 9.67 meters per second squared. That leads us to question 1-4. Do the two values for the gravitational acceleration agree with each other? Should they agree with each other? Yes, they do agree with each other. One is the average of the accelerations. The other is the slope of the velocity graph. They do tie together, especially since the acceleration is constant. Question 1-5, what is the meaning of the other constant in the fit equation for v versus t? The other constant is b, which is negative 1.93 meters per second. So that means that that is the y-intercept. Now, time 0 was when it started recording. But when it was recording, it was already falling. It didn't start recording until the ball reached about this height. At this point, then it was traveling at about 1.9 meters per second downward. So time 0, 1.9 meters per second downward, and it continued to go downward, increasing in its speed. It was almost at 5 meters per second by the time it hit the ground. So as you can see, the acceleration is very, very quick. In fact, if we let it fall for 1 meter, the object would fall about if we let it fall for 1 second, the object would fall for about 5.5 meters, or almost 5 meters. All right, now comes the tricky one. I'm going to do this one here. Let me turn off the smoothing, and turn off the line fit, and turn off the display, and turn off the stats function here. What I'm going to do with this one is I'm going to go ahead and go into activity 1-3, which is motion up and down. In that one, I'm going to take the ball, toss it straight up into the air, and hopefully it'll come straight down. It's going to take a little bit of practice, but the idea is we want to see what happens as the ball goes up, changing in velocity as it goes up, and changing in velocity as it comes back down. Prediction 1-3, suppose you toss a ball upward and analyze the motion as it moves up, reaches its highest point and falls back down. Is the acceleration of the ball the same or different during the 3 parts of motion? That is to say, moving upward at the maximum height and moving downward. And then prediction 1-4, sketch on the axes below your predictions of the velocity and the acceleration time graphs for this entire motion of the ball. Assume that the positive direction is upward, and we only want to look at the motion after the ball has been tossed up. So we're not looking at when I push the ball up, but after the ball leaves my hand. Now we're going to head and do the experiment. So let me reconnect the motion sensor. And I'm going to turn the camera a little bit so that we can see the landing pad. All right. Now this is going to be a little bit tricky. The way it's going to work is I'm going to have to take the ball, toss it up in the air, have it stay underneath the motion sensor the entire time, and have it come back down. It's going to be tricky. Really, the best way to do it is to practice keeping the ball over the yellow landing pad. I want to toss it as high as I can. If it was like that, I probably would get something. You see, I got to toss it. That might work. So we'll see what kind of data I get. Okay, so let's go ahead and try. I'm going to use my left hand to start and stop. I'm going to use my left hand to start and stop the recordings. So let's see what happens. Okay, let's try it again. All right. Oh, I remember what happened. I got to do one more little detail. I have triggers, software triggers put on, so I have to turn those software triggers off. Otherwise, we won't get any data whatsoever. All right, let's give it another go then. Not bad, but as you can see with the spike, it drifted outside of the view. So let's try it one more time. Now that one isn't going to work either, so we're going to do one more. Okay, that one will work. And how do you know? Well, let's take a look at the velocity graph. You see on the velocity graph, we have that nice slope right here. So that's a good velocity graph. Let's go ahead and zoom in, and we've got a really good acceleration graph as well. Okay, so let me go ahead and identify the points. This point right here, it's standing still. This is when I'm tossing the ball upward. And so as you can see, there's my positive acceleration as I'm tossing the ball upward, and then the acceleration drops down. Now the ball is, so let me rephrase that. On the velocity graph, here's where I'm tossing the ball upward. At this point, I've released the ball, and now the ball is still going upward because it's got the positive velocity, but it is slowing down as it goes up. At this point right here, we have 0 velocity. And then it starts to fall back down. And as it falls down, the speed is increasing. We have an increasing negative velocity until it gets to this point, and that's the point where the ball strikes the pad. We have the velocity comes back up to 0 at that point. So what I'm going to do to make it a little easier to do our calculations here is I just want to graph the motion of the ball itself as it's moving through the air. So first off, I'm going to eliminate a lot of the acceleration. So let me eliminate the acceleration data. Well, I can eliminate the velocity data too, so let's go ahead and start with that. So there's the velocity data. We'll go ahead and get rid of that. And then we'll get rid of this velocity data here. Now we're going to go ahead and do the same thing with the acceleration data. We're going to eliminate the data before the ball was launched. And then we'll eliminate the data after the ball struck the pad. All right, now let's get rid of the highlighter, and I can now rescale my, try it again. Get rid of this highlighter and get rid of this highlighter. And now I can rescale my graph to show the motion of the ball. All right. Okay, so there we go. We saw it was moving upward at 4 meters per second when it left my hand, and it hit the ground at just over 4 meters per second going downward. So there's the sketch you should make on the top of page 133. Let's go ahead and answer the questions. Oh, by the way, I can go ahead and put some text on it. So at this point right here, the ball is rising. Okay. Then let me move the bar here. Let me move that. Right. At this point right here, the ball has 0 velocity, so this is maximum height. And then at this point right here, I don't want to do that. I want to move, there we go. The ball is falling. So you should be able to identify those points. And the interesting thing is, I'll show you, let me show you with the graph, with the multi-coordinates tool. Here the ball is rising. It has a negative acceleration. Here the ball is at its maximum height. The velocity is 0. It still has a negative acceleration. And then here the ball is falling, and it has a negative acceleration. So keep that in mind. Question 1-6, compare the graphs to your predictions. In what way are they different, and what ways are they the same? Question 1-8, qualitatively come up with the acceleration during the 3 parts of motion. Okay, on the way up, on the way down, on the way up, the highest point, and on the way down. Explain your observations of the sign of the change in velocity as you did in lab number 2. And question 1-9, compare the portion of the acceleration graph when the ball was falling upward after reaching its highest point to the acceleration graph in activity 1-1 where the ball was falling from rest. In other words, this acceleration graph as the ball was falling compared to the previous one when I let the ball drop. And it turns out they're going to be the same graphs. So what are we trying to show here? We're trying to show that once the ball gets tossed up in the air, it has an acceleration. That acceleration is in the downward direction. It does not matter if the ball is moving up, if it's moving down, or momentarily stopped. It has an acceleration the entire time it is moving, as long as it is not in contact with anything. There's our little surprise there. Oh, by the way, what are the accelerations? We take the average of the acceleration lines, we get negative 9.74 meters per second squared. We take a line fit on the velocity graph, and we get negative 9.75 meters per second squared. That's a very, very close agreement between the two. Couldn't ask for much better results than that. Okay. Now, having seen all of that, I'm going to go ahead and skip extension. Let me go ahead and I'll go ahead and skip extension 1-4, but really, I can show you what happens when I take this coffee filter here and I let it drop. And as you can see, when I let it drop, it falls pretty much with a constant velocity as it goes downward. Now, here's where the things get interesting. Why does the coffee filter fall with zero acceleration? Well, we know we've got air resistance pushing up, so we've got a force pushing upward. The question is, what do we have pulling downward? We'll talk more about that in a moment. Let's go ahead and go into activity 1-5. That's on page 135. Prediction 1-5. Consider a very low friction cart moving up along an inclined ramp as shown. The cart is given a push up the ramp and released, and its motion is graphed using the motion detector at the top of the ramp. Okay? Sketch on the axes below your predictions of the velocity time and acceleration time graphs for the motion of the cart. Prediction 1-6. How does the magnitude of the acceleration compare to the magnitude of the ball as it free falls? So I'm going to reset the area, so I'll have a slope. I'll have the cart on a track, and then we'll test the predictions. All right. So now I've got the track set up here. We have the cart located down here. We've got the motion sensor set up here, and we're going to go ahead and do activity 1-5. Now again, prediction 1-5. What's the graph going to look like when I push the cart in the upward direction? It'll come to a momentary stop. It comes right back down, strikes the bumper here. So the question becomes, what is it going to look like? Is it going to look similar to the graph we see already displayed? By the way, the graph for that graph there, that's the ball being tossed straight up and come back down. Note what the acceleration is. It's somewhere around minus 10 meters per second squared. Okay, so we've got it set up. Let's go ahead and do the experiment on page 136. If the cart is, we've taken care of that, what we're going to do is we're going to give it a push and see what happens. So, well, that's interesting there. It looks very similar, doesn't it? Except the velocity is much, much less, isn't it? We have the same kind of slope. We have a similar slope here. We have a similar constant acceleration down here. However, the magnitude of that acceleration is much less. So what you need to sketch on the graphs are the region from about 0.4 seconds to about 1.5 seconds. In other words, the region where we have a constant negative slope on the velocity and a constant negative acceleration for the acceleration. What's the average acceleration? That's easy enough to tell. I'll go ahead and highlight that segment right there, use the sigma. We get an average acceleration of negative 1.76 meters per second squared. What about from the velocity graph? Well, I'll highlight where the cart was sliding up the ramp and use the line fit function, and I come up with a slope of negative 1.75 meters per second squared. So we see that the acceleration is much, much, much less. Why is the acceleration much less? Well, we did a problem with that in the class where we had the car on a sloping ramp. And we saw that the only force, that there was some kind of force, in this case the gravitational force, the weight of the car was pulling downward, but it wasn't just pulling straight downward. It was a component of that vector which was pulling it along the slope. And that depended upon the sign of the angle of the slope here. So let's go ahead and answer the questions, and we'll go ahead and finish up investigation 1. Question 1-12, did your graphs agree with your prediction? Does this motion appear to be constant acceleration? It definitely does. We can see the acceleration line is nice and flat. Question 1-3, how did the magnitude of the acceleration compare to that with the ball falling? Obviously, it's much, much smaller. The ball falling had an acceleration of around 9.7, 9.8 meters per second squared downward. This has an acceleration downslope of minus 1.5, 1.6 meters per second squared. Question 1 to 14, was this motion caused by the gravitational force? Yes, but it wasn't completely by the gravitational force, but by a component of the gravitational force that is parallel to the direction of the slope. Should the acceleration be the same as the ball falling? Definitely not. And again, all we have to do is do an analysis of the slope. Okay, we have the sloping line. Well, that's going to be tough to do, so I'll do an analysis when I go into investigation 2. In the meantime, if you have any questions, you know how to get a hold of me, and I will see you soon enough.